So, if we wish to name ionic compounds, there's a system we must employ, and we're going to start with the easiest cases, namely those ionic compounds that contain only monatomic ions. Monatomic ions are, of course, individual atoms that have gained or lost electrons so that they are positively charged, such as a sodium cation, or have negative charge to them, such as a sulfide anion. And if we're going to name ionic compounds containing ions such as these, monatomic ions, we should first take a look at how the individual monatomic ions are named. So, how do we name monatomic cations? Well, first of all of the monatomic cations, our job is made easier, are metals. And some of those metals, of course, are in main groups 1 and 2. Now, for all the metals in main group 1, they all have the same valence electron configuration. Namely, they all have a single valence s electron. So when these neutral atoms become oxidized and form a cation, they always lose just this one s electron. And consequently, every single element in group 1 forms only a +1 cation. Lithium, sodium, potassium, rubidium, etc. all form +1 cations. And then the same can be said of the group 2 metals to an extent. They all have an ns2 valence configuration. And as such, they all tend to lose both of their valence s electrons to form cations, and that's why, typically speaking, they will always have a +2 charge in their ionic state. Now, the same cannot be said for most of the transition metals, because while they do all lose their valence electrons in oxidation to become cations, some of them also have multiple states of oxidation. Namely, they form more than one charge as a cation. Iron is a good example. It forms both a +2 and a +3 cation. Other common examples are cobalt and nickel. They form also +2 and +3 cations. Copper forms a +1 and a +2 cation. So for most of the metals to the right of group 2, main group 2, there are more than one possible states of oxidation. Why is that important to us? The importance as to whether there is one or more possible charges for the ions that form from these metals has to do with how we name them. For instance, lithium cation is simply named the same as the element. It takes the element's name, lithium. And if you wanted someone to know you were talking about the difference between the cation and the neutral atom, you could add that to the term lithium. You could call this lithium cation. That's so someone wouldn't be confused with neutral lithium, the atom. Sodium, also in group 1, forms a +1 cation, and we simply call it sodium. That's its name, just as the element's name is sodium. Potassium is called potassium. The rubidium cation is called rubidium, and so forth and so on. Same is true of the group 2 metals that form cations. Magnesium +2 cation would simply be called magnesium, the same as the element. However, the difficulty lies with these transition group and even main group metals to the right of group 2, in that if they form more than one possible ion, for instance iron, which can be iron 2 or iron 3, simply calling the ion iron is not very helpful to a chemist, because they don't know which of the two iron ions you're talking about. So in the case of those metals that form more than one cation, the charge is written into the ion's name. This first would be called iron 2, and the second cation would be called iron 3. Now, when you do have to specify charge as part of the ion's name, it must be in Roman numerals and enclosed in parentheses. When I see the element's name followed by parentheses and a Roman numeral, I'm really being told what the ion's charge is. For instance, bismuth, if I saw this name in some substance, bismuth, parentheses, with a B, which is Roman numeral 5, I would know that they weren't talking about neutral bismuth, but rather they were referring to the bismuth plus 5 ion. If someone handed me a compound containing tin, and the first part of the name was tin 4, I would see that specified as part of the name. They're clearly talking about the tin plus 4 ion, because after all, there is also a tin plus 2 cation. So yes, naming monatomic cations, which these all are, is fairly simple if you just name the element. And in the case of almost every metal to the right of group 2, you'll also need to specify the charge of the ion in parentheses with a Roman numeral. Now, I say in almost all cases, there are some elements to the right of group 2 that have only one specific charge as an ion. And in those cases, you would not want to state the charge as part of the name. And the four most common elements that you're likely to encounter that do this are these three right here: aluminum, zinc, and silver. I know that's 3 and I said 4. Well, the one right beneath zinc, cadmium, is also very common. And you need to remember the charges that these 4 ions have on them as ions. Aluminum is the easy one to remember. It's in main group 3, and it only forms a plus 3 cation. And if you can count backwards down this diagonal line, you can remember that zinc only forms the plus 2 cation, and that silver only forms the plus 1 cation. And because cadmium is in the same group as zinc, it tends to behave chemically the same, and cadmium also only forms a plus 2 cation. So you can assume that at least in this class, any metal to the right of group 2 has multiple possible ionic states, and in writing the name of the ion, you would have to include the charge that these atoms had with them. In all cases except for these 4, you would never say aluminum 3, because just by saying aluminum cation, it is assumed that it's plus 3. It would be wrong to state the charge if there was only one. So in these cases, I'd be wrong to say lithium 1, sodium 1, potassium 1, rubidium 1. It's equally wrong for elements that have more than one possible charge as an ion not to state which one it is by not including parentheses and the Roman numeral for the charge. So for group 1 and group 2, you're safe. You name the ions the same way you name the elements. For all the remaining elements except for the 4 specified here, you need to include the charge as part of the name. So how do we name monatomic anions? That would be the next question then. And clearly the anions are all going to be nonmetals, those atoms with great tendencies to get reduced and form anions rather than the metals that tend to get oxidized and form cations. Well, that's a slightly different way to name anions. And for instance, I could list a few. Nitrogen's in group 5, main group 5. So it typically acquires 3 more electrons to get its octet and forms a -3 anion. So would phosphorus, so would arsenic, all in group 5. They all tend to form -3 anions. All those elements in group 6 tend to only acquire 2 electrons in reduction and form -2 charged anions. And then, of course, your halogens in group 7 all tend to acquire a single extra electron to achieve an octet and would form these anions. Now, on occasion, carbon will form an anion, and it would acquire 4 electrons as it's in group 4 and needs 4 more to achieve an octet. So essentially, when we're naming monatomic anions, here they all are. It's not a very large number of atoms you have to worry about. And the way in which you name a monatomic anion is you take the element's root name, such as fluorine for F, and you change the ending of the name to IDE, the suffix. So fluorine's a neutral atom, but as an anion we would name it fluoride. As a neutral atom, chlorine is Cl, but once it becomes an anion, we refer to it as chloride. Iodine becomes iodide. Bromine forms a bromide ion. Oxygen, oxide. Sulfur, sulfide. Selenium, selenide. Yeah, you get rid of the and replace it with ide. And tellurium, well, there's a town in Colorado named after its anion. That's telluride. And nitrogen would form nitride, and phosphorus would form phosphide, and arsenic would form arsenide, and carbon would form carbide. So yes, whenever you hear that IDE at the end of the name, you're no longer talking about the neutral atom, you're talking about its anion. So one last thing we need to know before we start naming various ionic compounds with monatomic ions is that the compound is always written in a chemical formula, and here's an example of one, AlCl3. And even though the individual ions in the compound have charges, the compound is always written so that it is neutral. And the reason this is neutral is because aluminum cations have a +3 charge. Let's not forget, aluminum's in group 3. If it forms a cation, it's +3. And chlorine atoms, when they form anions, and since they're in group 7, they always form the -1 anion. And for a compound containing aluminum and chloride ions to be neutral, you would need 3 of the -1 charged anions to balance the +3 charge on just one aluminum cation. So yes, they tend to accumulate in a crystal lattice in a 1:3 ratio. And that's why we write the formula for this compound as a 1:3 ratio, to get charge neutrality between the ions in the compound. So how do we name the compound? That's what we're up to here. Well, it's quite simple. To name an ionic compound, you just name the cation, and then you name the anion. In this case, the cation is aluminum. And of course, aluminum is one of those cations that always has the same charge, so I would not include the charge for part of the name. And the anions, even though there are 3 of them, I know are anions of chlorine, and we call monatomic anions, in this case, chloride. So this is the formula of aluminum chloride. In another example, if I say had this compound, well, I recognize it's ionic. It's got a metal and a nonmetal in it, and these must be monatomic ions. And so I would call the calcium ion simply calcium. It's always +2. It would be wrong to include charge in the name. And anions of bromine would be called bromide. Where it gets interesting is in a compound such as this, where I recognize that the cation is iron, but iron is one of those elements that could have one of 2 possible charges, so I would have to include the charge in the name. Now I do know the anions are chloride anions, so it's iron something chloride, and to figure out which iron charge this is, you look at the anions and determine their charge. Well, if we have 2 anions of chlorine that are -1 each, for neutrality, the iron has to be +2. Therefore, it's iron 2 chloride.